So in this video, I'm going to go through the reaction questions from exercise 1 of 25.3, which are about phenol. And I'm going to start on question 7 because it's a mixture of different functional groups and a mixture of different reactions that you've looked at throughout the course so far. So in your first one, 7a, you've got benzene reacting with nitric acid in the presence of sulfuric acid. This is a reaction you have to recognise. You're just going to redraw your benzene and you're going to draw it with an NO2 group. You can put that NO2 group anywhere on the ring. The next one, again, you've got benzene. Again, that's going to be your nucleophile, and you are reacting it with an acyl chloride. It's an acylation reaction. The carbon that is bonded to the oxygen and bonded to the chlorine is the carbon that is going to be attacked. So when I'm drawing my product, I'm redrawing my benzene ring. I can put the substituent anywhere on the ring, and it's going to be the benzene bonded to this carbon right here. This carbon is bonded to 2 other carbons, so 1, 2 others. So I've got 3 carbons in a chain, and this carbon is double bonded to an oxygen. Now it's also bonded to a chlorine, but here carbon has 4 bonds, and if it's going to form a new bond to the benzene ring, one of the old bonds must break, and it's that carbon-chlorine bond that breaks, which means chlorine is not part of my organic product, but the rest of the structure from the acyl chloride is still present. You end up losing a hydrogen from the benzene ring, so that hydrogen will pair up with the chlorine from the acyl chloride, so I have HCl. Actually above here as well, I could write H2O as another product. The next one then, I've got benzene reacting with Cl2. So the first one was Friedel-Crafts acylation. Now I've got Friedel-Crafts alkylation. So I'm adding, no I don't. This has nothing to do with Friedel-Crafts. I'm just adding chlorine to benzene. And again, it's a substitution reaction. Chlorine takes the place of hydrogen. You remove the hydrogen and you form HCl. The next one involves, so I've got my benzene ring and I've got an alcohol. So this is not a phenol because the OH is not directly bonded to the ring. So I've just got a normal alcohol and I'm treating it with potassium dichromate and sulfuric acid. So these are your oxidizing agents. And to be fair, I actually haven't told you whether it's distillation or reflux, which matters because I've got a primary alcohol, and if it was distillation I'd end up with an aldehyde, and if it was reflux I'd end up with a carboxylic acid. So I'm just going to assume that it's distillation, and I'm going to turn this alcohol into an aldehyde. So I've still got 1 carbon, and instead of being single bonded to an OH, it's now double bonded to an oxygen and single bonded to a hydrogen. So that's my product there when I oxidize my primary alcohol. The next one, I've got an alcohol again. Again, that OH is not directly bonded to the benzene, and I'm treating the alcohol with an acid. This is going to lead to dehydration, so I'm going to lose the OH from the alcohol, and I'm also going to lose a hydrogen from an adjacent carbon. The carbon bonded to the OH has got 2 adjacent carbons. It can lose a hydrogen from this carbon, or it can lose a hydrogen from this carbon. And that means I'm going to have 2 potential products. So if it were to lose a hydrogen from this carbon here, closest to the benzene ring, I'm going to form an alkene there. Or if it lost the hydrogen from the carbon furthest from the benzene ring, I would have an alkene there. My other product is going to be water because I'm losing hydrogen and OH, so I'm losing water. And that came up in the alcohols topic in chapter 14. The next one was another one that came up in the alcohols topic. This is going to be a substitution reaction, and what I'm going to do is I'm going to replace the OH group with the bromine group. So this is another example of an equation you need to know. So when I'm drawing my organic product, I'm just drawing the benzene ring again. I'm still drawing that carbon, and then instead of having an OH, I'm having a bromine, and this is a substitution reaction, which we looked at either in chapter 14 or in chapter 15. The other products you get is you're obviously losing the OH. That OH takes 1 of the hydrogens from the H2SO4 to give you H2O, and you also form H NaHSO4. When you remove the hydrogen from H2SO4, it's H minus SO4, and then the sodium has a positive charge, so they pair up together and they are the products that you get. The next one, I've got a phenol and I'm reacting it with nitric acid. Now, we've seen above that when you react with nitric acid, I'm adding an NO2 group to the ring, but in this case, because I already have an OH group on the ring, not every carbon is the same, and it does matter where I put the NO2. So with phenol, and we'll see this in the next topic, phenol always sends its substituents to either carbon number 2 or to carbon number 4. You're going to have two potential products. The NO2 goes next to the OH, and it can be on either side because both of these carbons are equivalent. So I could go there or there. It would still be one carbon away from the OH, so it will be carbon number 2. Or I can go to carbon number 4, which will be on the opposite side of the ring from the OH. So again, if I name this, I'd be naming the phenol carbon as number 1. And if I go around the ring, I can see that this carbon here ends up as number 4. Okay, if I went around the ring and numbered it the other way, that would also be fine. So that's question 7. I'm also going to do question 14. I'm not going to do the other ones. So in question 14, I tell you that phenol undergoes electrophilic substitution, okay, which is what we've just looked at, but it can also react through the oxygen lone pair. So essentially, when you've got a phenol, you've got two nucleophiles. You've got the electrons in the benzene ring that can act as a nucleophile, but you've also got a lone pair of electrons on the alcohol, which can act as a nucleophile. And in this question, I'm telling you that instead of using the benzene ring and forming a carbon bond with your electrophile, you're going to lose the oxygen as your nucleophile, and it's going to be the one following or forming the new bond. So in this case, my oxygen is going to be my nucleophile, not my benzene ring. If that's my nucleophile, I need an electrophile. Again, we've seen with acyl chlorides that it's this carbon here that always gets attacked. So it's going to be the oxygen attacking that carbon. You don't need to draw any arrows. You haven't been asked for a mechanism. So I'm going to have a new bond between my oxygen and my carbon. So I'm going to redraw out my ring again. I'm going to put on my oxygen. Oxygen can only have two bonds. At the moment, it's already got two, one to the ring and one to the hydrogen. So in order to form a new bond, one of its original bonds needs to break, and it's the oxygen-hydrogen bond that's going to break, so I'm not going to be drawing the hydrogen on oxygen anymore. Instead, I'm going to draw that oxygen bonded to this carbon, okay, my electrophile. I'm going to draw a bonded to that carbon, and then this carbon here, I need to look at what it is bonded to. So it is bonded to another carbon, and it is double bonded to an oxygen, and it was also singly bonded to a chlorine. But remember, if it already has 4 bonds, in order to form a new bond, one of the original bonds must break, and it's the carbon-chlorine bond that always breaks with an acyl chloride, and this is your product. Then you get the hydrogen from the OH and the chlorine from the acyl chloride pairing up, and you're always forming HCl. Okay, so this would be an example of an ester, a functional group that we study in more detail in chapter 26. The next one is going to be the same. I've got the lone pair on my phenol. It's going to be my nucleophile, and that delta positive carbon is going to be my electrophile. So I'm drawing out my ring. I'm putting in my oxygen. I'm not drawing in my hydrogen. And I need to look, and sometimes it's easy to miss out a carbon. So what I'm going to do is I'm just going to number them for myself, 1, 2, and 3. And I can see that carbon 2 is bonded to another carbon. So I'm going to draw oxygen bonded to carbon number 1, which is bonded to carbon number 2, which is bonded to carbon number 3. And again, I'm just going to number those for myself, 1, 2, and 3, where, corresponding to these 3 carbons here. And I can see that my original carbon 2 had a methyl group, which means it must still have a methyl group. Carbon 3 wasn't bonded to anything else. Carbon 1 was double bonded to an oxygen, single bonded to a chlorine. If I tried to fit all of those bonds back in, I'd have too many, and it's the chlorine bond that I don't include. And again, the hydrogen from the OH and the chlorine from the acyl chloride pair up to form HCl. And then here, this last one, I mean, it is exactly the same, even though it looks harder. Okay, so I've got my oxygen lone pair, going to be attacking that carbon there. And again, because this one's quite large, I'm definitely going to be numbering my carbons here. the main carbons in my chain to make sure I don't leave anything out. So I'm going to draw the product just under here where I've got space. So I'm going to be drawing my ring with my oxygen, and this oxygen is forming a bond to carbon number 1, which is in a 5-member chain. So I'm going to draw 1, 2, 3, 4, 5, and then I'm going to number those as well, and then go back and fill in the other groups that I need to. So on carbon 1, I can see I've got a double bond O, and I'm not going to be including that chlorine because I know it gets lost. On carbon 2, there's nothing. On carbon 3, there are 2 methyl groups. On carbon 4, there is 1 methyl group. On carbon 5, there is nothing. And my other product is HCl. So with these kind of like larger acyl chlorides, I would definitely recommend numbering the carbons in your chain to make sure that you have everything in the right place. It doesn't matter how kind of ugly your product looks if you have it all twisted and weird and not how it's conventionally drawn. As long as you've got all of the atoms bonded and in the right place, it doesn't matter if it looks a little bit weird. The next part of this was the acidity of phenols. I'm just going to go again through the reaction questions. I'm not going to go through the written questions because you do have the answers. So in all of these, you have to remember that your phenol does act as an acid. So these are just acid-base reactions. So the first one, actually, I've got a carboxylic acid. I'm reacting that with sodium hydroxide. If you're reacting acid and a base, you are going to form a salt and water. And because your carboxylic acid is an acid, remember, acids always donate H+, so the carboxylic acid loses H+. When it does that, that oxygen is left with a negative charge, and the sodium with a positive charge is attracted to it, and you end up with ONA, and then that's your salt, and you also get water. Phenol is going to do the same thing. Phenol can also act as an acid. It is a weak acid, but sodium hydroxide is a strong base, and they do react. So similarly to your carboxylic acid, phenol has to give up a H+, and it's the hydrogen from the oxygen that it loses. When it loses that H+, I'm left with O-. That O- is attracted to the Na+. And then again, the hydrogen from the OH pairs up with the OH from the sodium hydroxide to give me H2O. So I'm getting a salt and water. The next one, I've got a carboxylic acid. So I've got an acid, but this time I've just got a metal. So when you react an acid and a base, you get salt and water. When you react an acid and a metal, you get salt and hydrogen gas. So salt is going to be exactly the same as what I saw in question number 1. But now, when you kick off the hydrogen, I don't have an OH to pair up with, as I did in A and B. So the hydrogen's left by itself. Hydrogen is diatomic, so I'm going to have to write that as H2. And then your last one, you have got your carboxylic acid, you got sodium carbonate. So sodium carbonate is a weak base, but carboxylic acid is strong enough to react with it. So again, I'm going to draw my carboxylic acid. It's going to be losing H+, and it's going to pick up a sodium, and I'm going to form H2O, and I'm also going to form CO2 because it's a carbonate base. I'm going to form CO2 as well. I haven't balanced these equations, but you can go back and balance them yourself.